Hello, I wanted to produce a video that gives you some help with our homework problem 8.33. I get quite a few questions about this problem, and I thought this would be helpful to you. I'm going to demonstrate a couple of the methods of how we solve that homework problem, but using it for a different set of data. So that problem has to do with acceleration and determining the distance that something has traveled within a certain amount of time. I thought to do that, it would be interesting to look at the car that currently has the record for the highest acceleration. That is the Porsche 918 Spyder. So this is the fastest car to 60 miles per hour ever in Motor Trend's independent tests. And I have the starting price in there of $845,000 for a starting price. But you all will have that soon, right? After you graduate, you'll be making the big bucks. So let's look at this car. So first here we have some of the specifications of the performance of this car. So it is powered by a naturally aspirated 4.6 liter, 4,593 cc V8 engine, developing 447 kilowatts, 599 horsepower at 8,700 RPM. You can go through this. So that produces almost 600 horsepower. And then they have two electric motors that deliver an additional 282 horsepower. So combined, that's 875 horsepower. It's a lot of power. That's 944 foot-pounds of torque. Let's see. So it delivers an all-electric charge range of 19 kilometers or 12 miles. So you can't go very far, but you can get there really fast. I took the data of how long it takes it to reach 100 kilometers per hour, 200 kilometers per hour, and 300 kilometers per hour. That's 2.5, 7, and 19.1 seconds. So like our problem, the question is, what distance did it travel? So here we see the published data, but we don't know how far it traveled. If you remember, our accelerometers lecture gave us these equations. It's just how to move back and forth between displacement and velocity and acceleration. Should be pretty familiar with these. Since we're interested in how far it has displaced and we have velocity data, this would be the equation we want to use in the red box. If I plot that data, this is what it looks like. That data isn't exactly like what we have in our problem. Our problem has defined intervals of time that are equal. So I converted this data over to that. So I adjusted for uniform time intervals. There's going to be a little bit of error associated with this, but this allows us to solve the problem in a way similar to what our homework problem is. So here we have the question a little more specifically, and that is, what distances did it travel at 10 and 20 seconds? There are two methods to solve this. The first would be the numerical method. We have this data that's been collected, so numerical method makes sense for that. The trapezoidal rule is one option for doing this. Appendix A in our textbook walks you through how to use the trapezoidal rule. It does it in terms of doing a Fourier series transformation. But the same method can be applied here. Here is that equation. So if we have an integral, or if we want to take the integral of some data, so that data that we have, the velocity data, that's that g of t. And we want to integrate over a certain time from a to b. So if we do that, then let's say the way that we would do that is what is on the right side of that equal sign. So we take the difference from our ending to our starting point. We divide that by 2 times the number of intervals that we have. And then here we just have each of the data points. So the 2 on the ends, they're just there themselves. But each of the ones in between, these are all multiplied times 2. So essentially what you're doing is you're creating trapezoids for each of those different intervals. Now here we will apply it to our data. And this makes a little more sense if we convert the velocity to meters per second. It'll make it a little bit easier to compare to some published data so we know we're on track. Here we have again an equation. So if we first do the distance traveled in 10 seconds, so we go from 0 to 10, and there are 2 intervals, right? So 1, 2. 0 is the first one, and 64 is the last one. We don't multiply those times 2. And the one in the middle, that one does get multiplied times 2. So pretty simple, just plugging those things in, we solve it, and we get 390 meters. As you likely know, that is very close to a quarter mile, right? 1,600 meters is a mile, so 400 meters is a quarter mile. And this car has been tested. So the quarter mile time is a fairly common test for cars. And this one got to a quarter mile in 9.8 seconds. So here, our equation, our calculation found at 10 seconds, we're at 390 meters. So here, 9.8 is pretty similar, 390 is pretty similar. Like we said, there's a little bit of error because we didn't have the exact data. We had to adjust it a little bit. That's likely where this error comes from, but it's still really close. We know we're on track. And then if we did the same thing for where it would be at 20 seconds, we just put in 20 here instead. We have the number of intervals has been increased to 4. And then we have, well, the 64 is now in there twice because that's one of the intermediate values. We just have our 2 at the end. They're in there without being multiplied times 2. And then each of the intermediate points are multiplied times 2. We end up getting 1,125 miles, or a little under 3/4 of a mile in 20 seconds. The other method is direct integration. So here we have that data published, and what you would do in this case, there's going to be some error associated with this method too, but what we did was get a line of best fit. So we did second order polynomial. We get this equation here. That's this dotted line. So you see, so this probably matches pretty closely. And up here, it's going a little bit above the value and coming back down. We know that's not real. I mean, this is going to be a little bit closer there, but this should at least get us into the ballpark. It should be a pretty good estimate. So here we will actually solve that integral. So we put that line of best fit in here. We integrate with respect to time, and this is what we get. And we were at 0.0 in terms of displacement, so that just drops out. So if we solve this for 10 seconds for our time, we get 415 meters. So again, really close to that quarter mile, just a little bit on the other side of it this time. And then at 20 seconds, we're at 1,237 meters, which was also pretty close to what we calculated the other way. Here we have those values in the table. So these pretty close, this bigger difference, this is probably more of an overestimate from that increase there. I would say that the numerical method was probably better. If we had a line of best fit that was more something like that, that would probably be the best option. But we have a little bit of error in both cases. Using the trapezoidal rule, the numerical method is probably better. So hopefully that's helpful in you solving the homework problems.